Imagine scrolling through deep space. 2,000 points of light. Sorted, filed, accounted for, ready. And then 9 of them refuse to fit anywhere. Not stars, not quasars, nothing we already have a name for. Their light traveled almost 13 billion years to reach us, since the universe was in its infancy. And when scientists finally broke that light apart into a spectrum, the answer didn't match a single line in the tables humanity has been building for decades. Even the researchers who found them couldn't agree on what they were looking at, so they gave it a nickname instead. And the nickname says everything. In early January 2026, at the American Astronomical Society meeting in Phoenix, an astronomer stepped up to the podium with a slide showing 9 small gray squares. Nothing impressive to look at. But behind those squares were months of work by a team from the University of Missouri, scanning the James Webb archive almost by hand, eye by eye, one compact source of light at a time. The task started out simple: sort thousands of point-like objects in deep space images into 2 known categories: stars from our own galaxy, or quasars, the blinding cores of distant galaxies, powered by supermassive black holes. Astronomers have tools for this: color, spectral shape, the pattern of emission lines. The system has worked for decades. It should have worked this time too. The team ran nearly 2,000 objects through the filter. Most of them settled neatly into place. Stars here, quasars there. But then someone on the team started checking the results by hand, object by object, just to make sure the filter hadn't made a mistake. And that's where everything stopped. 9 sources of light didn't fit either category. They looked like a single point in the image, exactly the way a star or a quasar core looks. But something in their properties stubbornly refused to match any template. Refused so completely that the automatic classifier never even flagged them as a problem. It just filed them wherever there was a little room to spare, and got it wrong. They were only found because someone decided to double-check finished work with their own eyes. And here's the question the team still can't put to rest. If a well-tuned system, tested on thousands of objects, let 9 anomalies slip past every filter, and they were only caught through a manual check of a handful of images, how many more are still sitting uncaught, somewhere in the rest of the Webb archive, that no one has ever checked by hand? To understand what actually threw the researchers off, you have to look past the image itself and look at the spectrum instead, at how the object's light breaks apart across wavelengths. It's the only real way to determine the nature of a source sitting more than 12 billion light-years away, where no detail of shape survives the distance, just a point. Quasars usually show broad emission lines in their spectrum, the signature of gas spinning around a supermassive black hole at tremendous speed, smearing the line across the spectrum. The 9 objects had none of that. No broad lines at all. So, not quasars. But they did have narrow emission lines, a trait that usually points to active star formation inside a galaxy. That's exactly what light from a stellar nursery looks like. But a real star-forming galaxy should show a faint, diffuse outline, even just a little, even just around the edges. These objects had nothing like that, just a point, compact, sharp, as if there was nothing there at all except a single source of light. It's a strange combination. Narrow lines, like a galaxy, but the shape of a point, like a lone star or a quasar core. two traits that are common enough on their own, but together, they shouldn't exist at all. One researcher on the team jokingly compared the find to a platypus, an animal with a duck's bill, webbed feet, and yet it lays eggs like a reptile. No single trait is rare on its own, but together, they add up to a creature that doesn't fit into any biological category at first glance. The nickname stuck, except the platypus was figured out a long time ago. We know exactly which class it belongs to. These 9 sources of light? Not yet. Not one of the known galaxy formation scenarios, built up over 30 years of observation, ever predicted that this particular combination of traits could even appear at this point in the universe's history. And yet the team didn't stop there. They tried to explain it anyway. And what they came up with is bold enough to rewrite what we think we know about the early universe. When an object refuses to fit into existing categories, astronomers have only one option: propose a new one. The team put forward 2 explanations, and either one could rewrite what we think we know about the early universe. First, this is a previously unknown type of active galactic nucleus, a compact, narrow-lined engine, hiding a galaxy so faint it simply doesn't show up against its own bright core. A black hole in disguise as a star. Second, these are extremely young galaxies, less than 200 million years old. They're forming so fast and staying so compact that they simply haven't had time to spread into the shape we expect a galaxy to have. Neither explanation closes the case completely. If these are a new kind of active nucleus, why are there so few, and why now, in this exact era? If these are ultra-young galaxies, why is their spectrum so clean of the dust and gas that should come with star formation this intense? And this isn't the first time JWST has broken expectations for this era. The same telescope has already found blue monsters, too bright, too compact for their age. It's found little red dots that also refuse to fit standard black hole models. Any one anomaly on its own could be a fluke. But when too many show up in the same slice of cosmic history, coincidence stops being a convenient answer. And the Missouri team only checked a small fraction of the images already sitting in Webb's archive by eye. The 9 anomalies weren't found because anyone was looking for them. They were found because someone decided to double-check the algorithm's work by hand. Automated systems find what they already know how to look for. An object with no label just quietly settles into the nearest available bin and stays there, unnoticed. We don't know if we're looking at a new class of object that will rewrite the textbooks, or simply the limit of what we're able to recognize in light collected from the deep past.